Hello and welcome to this lecture. This is chapter number 8, second order circuits of our Sadiku's textbook. In this lecture, we'll be talking about the step response of a parallel RLC circuit, a brief overview of our previous videos and lectures. In our previous videos, we have seen how we solve the second order circuits, how we solve second order differential equations, and then we saw our first case was source free RLC circuits in series, source free RLC circuit in parallel. Then we talked about how we develop or how we analyze the response of a series RLC circuit for a step input. Today, we'll be talking about how we analyze the circuit or a parallel RLC circuit for a step input response. So here what we see that we have a parallel combination of a resistor, inductor, and a capacitor, and there is a current source that is attached to it. And as soon as time t equals to 0 uh, occurs, the switch is thrown and the current source gets in parallel with the RLC circuit. So let's solve this circuit. So at time t equals to 0, we have to basically develop the differential equation for this circuit. So this differential equation for this circuit can be easily developed using the KCL or the Kirchhoff current law or KCL. And for writing the KCL or the current equations, this whole part is basically considered as at the same voltage potential, because all these resistor, inductor, and capacitor are connected in parallel. So the potential across these 3 points will be the same. We consider it as V, and the current entering this node, or we can call it as super node, is IS. So writing the overall equation, we get basically current through the resistor V divided by R, plus current through the inductor, that is given as I, plus current through the capacitor, and we know that IC is given as C times dV by dt, and the capacitor voltage is V. So C times dV by dt, and these are the current that are flowing out of these nodes, and current entering this node is equal to IS, and I call it as IS. Now, we also know that the voltage across the inductor is given as VL times di by dt, and we use this equation. This is say our equation number 2. This is equation number 1. So by using equation number 1 and 2, we get this equation. And let's see how we get this equation. So wherever we have the voltage sign, replace the voltage sign by L times di by dt. So for here, I can replace di by dt divided by R plus I as it is, C times d by dt multiply by L times di by dt equals to IS. And if I simplify it, we get so basically divide the whole equation by LC, we get something like di square by dt square plus I divided by LC plus this. If I'm writing this term over here, so divide by LC, it becomes 1 by RC di by dt, and again we are dividing, so this is a term also. So this is basically a simplify how we get this equation. So now when we solve this differential equation, we basically have two solutions for that. So one is the transient case, and the other is the steady state case. Steady state. So there, the solution set for this sort of differential equation has two parts, and the overall solution is the linear combination or the addition of both of these transient and steady state solutions. So let's see how we solve them. So for the transient case, we basically solve this differential equation, or we basically develop the characteristic equation, number one and number two, we solve the characteristic equation. You can call it characteristic equation. Solve the characteristic equation. We get, because it's a second order differential equation, the second it would be a quadratic equation, so we'll get two solutions. So the two solutions will be, we call it them S1 and S2, and these two solutions can be um, distinct and real, same and real. They can be imaginary, right? uh, or imaginary, you can we have both parts. It have a real part plus, this is a real part plus an imaginary part. So, or it's not imaginary, so we can call it as complex. And the fourth form is what we call it imaginary. And the imaginary will have only j beta 1. They will not have this minus alpha or alpha component or the real component event. So we are not in our this chapter, we are not basically concerned with the imaginary parts, because they give us the uh, oscillatory solutions, and oscillators are not a part or not the context of this topic which we are discussing. So we basically remain in this distinct, real, same and real, and complex and complex solutions for our differential equation of our characteristic equation. And from these solutions, we have seen that if our roots, or if the solution for the characteristic equation is distinct and real, the transient response looks something like this. So it is a1 e raised to power s1t plus a2 e raised to power s2t. Similarly, if the roots are same and real, the response is a1 plus a2t e raised to power minus alpha t. And similarly, if our roots are complex, our response is consists of it's something like this: a1 cos omega dt plus a2 sine omega dt e raised to power minus alpha t. And we and I suppose that you have seen how to come up with these solutions as a part of your mathematics course on differential equations. So moving ahead, so this is basically how we find out the transient solutions for that, and this is the same how we solved it for a series RLC circuit in our previous lecture. So for the step response, sorry, this should be parallel RLC circuits. So now how we develop, or how we find out the steady state response. So for steady state response, we basically have to see the response of this circuit after time. So steady state, we have to see after time t equals to infinity, or after a long time. So after a long time, or our assumptions are that inductors and capacitors are either completely discharged or demagnetized, or completely magnetized, or completely charged. Okay, so now what we do is we just put I equals to infinity. So at I equals to infinity, let's draw the equivalent circuit for this. So at I equals to infinity, we know that the resistor would look something like this. So inductor would be completely magnetized, so it will behave as a short circuit. Inductor will behave as a short circuit, and the capacitor will be completely charged, so it will behave as a open circuit. See, so this is how it would be. So at time t equals to infinity, the I value, or the current through the this branch, will be equal to whatever the source current or is is. So the inductor will be having complete is, so that is why this value of is will be the value for the steady state current for this circuit. Remember, this value will be different for different circuits. So for every circuit, you have to basically find out this value. So how our overall circuit looks like, again, this is parallel RLC circuit. So our overall solution will look like the steady state response plus the transient response. Remember, this is the steady state response and this part is the transient response. Same goes with these two as well. So this is steady state response and these are the transient response. And once we have this response with us, how we calculate the values of A1 and A2, the A1 and A2 will be calculated with using the, oh, sorry, this circuit is from the previous slide. So we have to basically, so this is not the circuit. So our circuit here is something like this. And this is IS, this is R, this is L, this is C. So we basically have to find, in order to find out the values of A1 and A2, what we have to do is that we have to find out the initial conditions for current I equals to 0 and current I dt. This. So we need to have these two initial conditions. So once we have these two initial conditions, we put it in this equation, we get two simultaneous equations, we solve these two simultaneous equations and we find out the values of A1 and A2, just like which we did in our last video. So now let's solve an example and see how this thing is done. So here in example 8.8 of your textbook, it says that in the circuit shown in the figure 8.23, find out the value of R. So we have to find out this value of R and we have to find out the value of I and find I of t. So I of t, we have to find out this value of I of t and IR of t, or the current through the resistor, for time t greater than 0. This is again an important aspect. So our first thing we have to do in this circuit, you have to find out the initial conditions. This is our first step. So for finding out the initial conditions, we have to first of all draw circuit for time less than 0. For t less than 0. So before time t equals to 0, we know that this switch is not closed. So our circuit was something like this. This is a voltage source 30 u of minus t. Remember, this is a voltage source that remains open, or 30 u of minus t. The waveform will look something like this, that before time t equals to 0, this is 30 volts, and after time t equals to 0, it is 0 volts. So it doesn't have any value. So this is how this voltage source looks like. So this is 30 volts. And we have to basically, so this is 30 volts. So we basically have to find out what is the value. So this is our IR. What is the value of this VC, or the capacitor voltage? So this circuit is in this state for infinite time, and we don't know how long it has been in this state. So say we can say that we are moving from minus infinity till the time we reached here. So we assume, or our good assumption is, capacitor would have been completely charged. So this capacitor would be behaving as an open circuit, and we have to find out this open circuit voltage. So this is 30 volts. So we have to basically find out this open circuit voltage. This is 20 ohm, this is 20 ohm, and VC, this is, so this VC is basically the voltage drop across this 20 ohm resistance. So VC at 0 negative is 20 divided by 20 plus 20 multiplied by 30. So this is 15 volts, VC 0 negative, or VC 0. And we also know that IC equals to C dV by dt. Capacitor doesn't allow instantaneous change in voltage across it. So therefore we can write VC 0 negative equals to VC 0 positive, or we can call it as our first initial condition equal to 15 volts. So this is our first initial condition for this case. Now we have to find out what is the initial condition for the current in this case? So initial condition of for the current. So with this, so before time t equals to 0, this is half of the circuit, and other half of the circuit looks something like this. So other half of the circuit will look something like this. So this is the current. This is 4 amperes. This is 20 Henry. Remember, there is this switch, and this is the other half of the circuit. So this switch is not closed. So this circuit will be acting independently, and this circuit will be acting independently. So this is 4 pairs. So this for an infinite time, this circuit or this capacitor, or sorry, this inductor will behave as a short circuit, or it means that it is completely magnetized. It means that the current stored in an inductor is equal to 4 ampere. So this 4 ampere will be flowing in this current. Again, remember that inductor voltage. So we know that inductor voltage is L times di by dt, and inductor doesn't allow instantaneous change in current. So we can easily write that I0 negative is equal to I0 positive. We can also call it I0, and this is 4 amperes. So this is our another initial condition that we will be using in this question. So now we have first two initial conditions with us. Now the second part, we have to solve the circuit. So second part, solving for t greater than 0. So for t greater than 0, the circuit will look something like this. So we have this current source that comes in parallel with this resistor, capacitor. Oh, sorry, this is a capacitor here, resistor. This is a capacitor here, and we have a another resistance, because this voltage source won't be there, but this resistance is there. So this, we just simply short this voltage source. This is 20 ohms. This is capacitance C. This is again 20 ohms, and this is our inductance of 20 Henry. This is the current that is flowing through the conductor. This is IR. This is plus minus V. This is 4 ampere. So this is how our circuit look like. So first of all, we have to find out alpha, since this is a parallel RLC circuit. So the alpha for a parallel RLC circuit is 1 over 2 RC. So what is the, so R equivalent, or the total R for this circuit? So the total resistance is basically 20 ohms in parallel with another 20 ohms. So the effective R equivalent is 20 multiplied by 20 divided by 20 plus 20. This becomes equals to 10 ohms, and that is the equivalent resistance. So basically we have two 20 ohm resistances in parallel, and that makes the resistance as half of what it actually is. So what do we get? 1 by 2 into 10 multiplied by capacitance. The capacitance is 8 millifarad. So the value of alpha becomes, oh sorry, my bad, this is R equivalent I am writing here. So the R equivalent value is 10 ohms. So alpha becomes 1 divided by 2 multiplied by 10 multiplied by 8 millifarads. So this value becomes 6.25 seconds minus 1. We have the value of alpha. We have to find out omega naught. Omega naught is 1 by under root LC. So 1 by under root LC, inductance is 220 multiplied by capacitance 8 millifarads. So when we find out the value, this value comes out to be 2.5 radians per second. So now what we have alpha greater than omega naught. So when we have alpha greater than omega naught, remember from here that we have a overdamped response. So this is the first case of what we get. So alpha greater than omega naught, we have a overdamped response. The other easier way is to just simply find out Number 3, find a solution, or find, you can say, roots of the characteristic equation. So finding out the roots of the characteristic equation, we say that S1 and S2 are the two roots. It is minus alpha plus minus under root alpha square minus omega naught square divided by, no, yes, so not this. So this is how we find out the roots. So just simply putting in the values of alpha and omega naught, we find out that roots become minus 6.25 plus minus under root 6.25 square minus 2.5 square. The values of S1 is the minus 11.978. We get one value, and for S2 we get minus 0.5218. So these are the two values for S1 and S2, and we can say from here that these two values are real and distinct. So when we have real and distinct roots of the characteristic equation, our response is a overdamped response. So generally we can write that response as I of t a1 e raised to power s1t plus a2 e raised to power s1t and s2t. So this is the transient response, initial transient response for our case. Okay, so now let's find out 4-part solve for I for time t equals to infinity. So now infinite time has passed. So this circuit would look something like this. 20 ohms. Sorry, there is an inductor here, 20. This is a capacitor here, and there is another resistance here. This is 8 millifarad. So this is how the circuit would look like, or its equivalent circuit will look something like this. So I make a resistance of 10 ohms. My capacitor inductor will behave as a short circuit, and my capacitor will behave as a open circuit, right? So this is how the circuit would look like, and this is value of Is, and this is equal to 4 ampere. So the current through the inductor I, so I at infinity will be equal to 4 amperes. So my I at infinity is equal to 4 amperes. So my overall solution, will be I of t transient solution plus I of steady state solution. So my transient solution was a1 e raised to power s1t plus a2 e raised to power s2t plus the steady state solution of I of infinity. Now putting in the values, my I of t will be say 4 amperes from this, a1 e raised to power minus 11.978 t plus a2 e raised to power minus 0.5218 t. So this is how my solution will look like. Now what we have to do? Now we have to basically find the, this is the step 5, find the, so I call this as equation A. Find the second initial condition. For the second initial condition, that is di 0 by dt. This is what we have to find out. Okay, so now we know that VL equals to L times di by dt. And what is the value of VL at 0? This is we have to determine. So voltage across the inductor at time t equals to 0. So this is we have to determine. So let's go back to the previous slide here, or even one before that here. So this is the initial case. We found out that the capacitor voltage was 15 volts, or the voltage appearing across this capacitor was 15 volts, and the current through this inductor was 4 amperes. These were our initial conditions. So what will happen? Let me draw it in. So uh, let's see how the circuit looks at t equals to 0. So the circuit looks at t equals to 0 is something like this. Inductor is here, resistor is here, my capacitor is here, my another resistor is here, right? So this is 20 ohms, this is 8 millifarads, this is again 20 ohms, and this is 20 Henry. Okay, and this is having I0 as 4 amperes, and this is having V0 as 15 volts. So now what will happen, or what will be the voltage across this two terminals? Let me call it A dash. So voltage across, so inductor is, sorry, A dash, and this is basically all these components are in parallel. So whatever the voltage across the capacitor will be the voltage across the inductor. So this is equal to VC at 0. So the voltage across inductor initially will be 15 volts when the switch is on, when the circuit is switched on, right? So our switch is somewhere here. So at t equals to 0. So this is 15 volts. So now if we have to find out di by dt at time t equals to 0, we know that VL equals to L times di by dt, and using this equation, if at time t equals to 0, this thing can be written as this. So from there, I can easily find out my di by dt at 0, and this value will be 15 divided by 20, and 0 point or 3 by 4 or 0.75. Again, this is amperes per second. So this is the value, or this is the second initial condition which we will be requiring. So let me write it over here. So di 0 by dt equals to 0.75 amperes per second. This is my second initial condition. So now step number 6, find values of A1 and A2. So finding out values of A1 and A2, first, we know that our solution was I of t 4 plus A1 e raised to power s minus 11.978t plus A2 e raised to power minus 0.5218t. So this is my first case. So for first equation for t equals to 0, what we get? I of 0, 4 plus A1 plus A2. And from here, I of 0, we remember our first initial condition, I of 0 is equal to 4. So from here, we can find, we simply say that 4 is equal to 4 plus A1 plus A2. So A1 equals to these 4 basically cancels with each other. So we get A1 equals to minus A2, or A2 equals to minus A1, or vice versa. Any of these conditions would be fine. So then for t equals to 0, again di by dt case. So just simply differentiate it. If we differentiate our top equations, we get 0 plus minus 11.978 a1 e raised to power minus 11.978 t, again minus 0.5218 a2 e raised to power minus 0.5218 t, right? And again putting time t equals to 0, what we get? We get another differential equation, and that differential equation uh, gives us so we have 0.75 as d by value of d by dt. We get minus 11.978 a1 and minus 0.5218 a2. So this is my one differential equation, oh sorry, one equation, and this is, I call it as 1, I call it as 2. Now solve 1 and 2. We get a1 say equals to minus 0.0655 as a1, and a2 will be 0.0655, right? So these are the two values for a1 and a2, what we get after solving these two equations. Okay, so now our overall result I of t will look something like this. I of t 4 plus a1. A1 was minus, it comes with a minus sign, so so I can write it as minus 0.0655 e raised to power minus 11.978 t plus 0.0655 e raised to power minus 0.5218 t. So this is how my solution for this thing will look like. Okay, so this is I of t. I can write I of t as this. So this is the current through the inductor. Now basically I have to find out IR. So for IR, I need to know the voltage across, or VR, and I have to basically divide this VR by the value of resistance. And what is the value of, or what is the voltage that will be appearing across this? So remember, the voltage uh, across the inductor VL is given as L times di by dt, right? So if we just simply differentiate this equation, so we will get so, so if we differentiate this equation and multiply by with the value of inductance, we'll get the voltage across the inductance, and that will be the voltage that will be appearing across the resistor, right? So just simply if we differentiate it, so di by dt, it becomes minus 0.0655 multiplied by minus 11.978 e raised to power minus 11.978 t plus 0.0655 multiplied by minus 0.5218 e raised to power minus 0.5218 t. So if I solve it, this will be solving it will give me the value. And if I have to find out IR will be VR, oh sorry, IR will be VL divided by R, and VL is basically L times di by dt divided by R. So multiply by the inductance value. So inductance is 20 Henry, and overall resistance is again 20 ohms. So inductance value is 20 Henry, resistance is 20 ohms. So what we are left with, we are left with this di by dt here. So overall, what we get is 0.785 if we multiply both them, e raised to power minus 11.978 t minus 0.0342 e raised to power minus 0.5218 t. And this is the value of IR, again in amperes, that is flowing through the resistor of 20 ohms, right? So this is how we calculate our answer. So this is our answer, and again this is our answer. So we are required to find out the value of I of t. We have found out the value of I of t, or that is the current through the inductor. And similarly, we are required to find out the current that is passing through the 20 ohm resistor. So we have found out the current which is passing through the 20 ohms resistor. So this is how we solve a parallel RLC circuit for a step response. So I hope you understand this topic or this section, and hope see you next time, hopefully. Thank you very much for listening.